So this is the third lecture of solid state physics, and when we have studied the single crystal and polycrystalline solids, we can now study the crystal structure, and we are concerned with the structure of the crystalline solids, or I should say the monocrystals or the single crystals. And this structure is very important whenever you are studying solid state physics. Crystal structure is the main component of the study of structure of the crystal systems. So to begin with the complex theories of crystal structure, let us first understand why the structure is important. And we will see that this word repetition or periodicity or symmetry, they are the fundamental basic of the crystal structure or the structural study of the solids. Now, why the study of the structure is important? In this diagram, you can see there are three, I have numbered them 1, 2 and 3. There are three pieces of solid. One is totally transparent, 2 is translucent, and number 3, it is totally opaque. You will be surprised to know that these three pieces of solid are of the same material, aluminum oxide. It is the same material, aluminum oxide. The first specimen is transparent, the second is translucent, and the third is totally opaque. Now, what is the difference if the composition is same? The difference is that the first crystal, it is a single crystal of Al2O3, which I have explained in the previous lecture, that a single geometrical pattern repeats in 3 dimensions. A single geometrical pattern, you can say geometrical pattern or arrangement of atoms pattern or array of atoms. You can also use this word, array of atoms, repeat in 3D. This structure, single crystal structure, due to its periodic arrangement of atoms or periodic arrangement of the units that are forming this crystal, allows light to pass through, and it is transparent in nature. It is transparent in appearance. The second thing that you are observing here, the second one is polycrystalline material, polycrystalline aluminum oxide. And as I told you in the previous lecture that there are grain boundaries. The grain boundaries inside this polycrystalline aluminum oxide, Al2O3, they scatter the light and it makes the system translucent. How? Scattering of light so that it is translucent. And the third one is the aluminum oxide that has many defects or voids, empty spaces. We will study the defects later. So a same material, aluminum oxide, can be found in 3 forms: translucent, transparent, opaque, and it is all related to the structure of the aluminum oxide. Moreover, I told you in the previous lecture that the DNA, human DNA, it is composed of, it is also a crystal. It is also a crystal structure, and it was studied, and it was a revolutionary experiment in physics, in material science. And that DNA is different for every person. The structure is different for every person. So the total study of crystals is focused on their structure, because all the properties, not most of the, all the properties are due to the structure. So it is very essential to study the structure in a scientific manner. I will tell you more practical applications regarding this. So what happens in a crystalline material or a pure material? Many times it is written in the textbooks, pure material. The atoms are arranged in a periodic structure or arrangements that repeats over to long distances. And this repetition to long distances, it is called long range order. And what we mean by distance here? Here distance means atomic distances. Atomic distances in angstrom units, not in meter and kilometer. It is angstrom unit. Atomic level ordering is there. When these materials, they are solidifying, or when the atoms are coming closer to solidify to produce a structure, the atoms arrange themselves in a 3D structure, with the speciality that particular units, they are repeating itself throughout a 3D pattern. You can imagine this, that you have a 3-dimensional room and you are laying tiles on the floor of the room, and you are stacking the tiles on the floor also. So the entire floor is filled with same type of tiles. And I showed you the diagram of Rubik's cube. That is the best representation of a single crystal, where same geometrical pattern is repeating throughout the structure. Now let us first learn some important properties of the crystalline materials that will help us in understanding the structural study before going to the structure. So the first important physical property of crystalline material is that they have macroscopic homogeneity. Homogeneous means same composition. Homo means same, and geneity is related to the composition. So what happens here, all the properties of the crystals, they are same in all its parts. Suppose if you have a crystal like this, and this is part 1, this is 2, this is 3, this is 4. The properties of part 1 are same as that of part 2, part 3 and part 4. It is not that some property of part 1 is different from part 4. Every single piece of the crystal, when you study its properties, the composition is same. That is called macroscopic homogeneity. And this type of property of crystal, it is described by a mathematical tool that is called tensor. We will come to the analysis later on. Suppose you take a crystal for any experiment. Suppose it is a quartz crystal, or any crystal. Quartz is mostly used. You can have a piece of diamond also. Then what you have, you are holding the piece of diamond or piece of quartz with a pair of forceps or in your hand. So the piece of that material is, of course, its dimensions, its length, its area, its surface area, they are larger than the atomic dimensions. So if your atomic dimension, what I mean by atomic dimension, suppose it is B, means after B distance, if these are the atoms and this distance is B, this pattern is repeating after distance B. Again you have this kind of a pattern. Again after this distance B, again you have this same kind of pattern. This is called the atomic distance or the order. What I was saying, the order is this. So what happens, that crystalline homogeneity implies that if we are measuring a particular property F, then this property will be same in all directions. Mathematically, if you are measuring the property at some point whose coordinates are x1, x2, x3, and you shift the origin by a small amount, so that your x and y and z coordinates, or all the three coordinates, they are changing by x1 plus x1 dash, x2 plus x2 dash, x3 plus x3 dash, then at these 2 points that are nearby each other, or that are produced by the small or arbitrary translation of the origin, these two properties are same. At x1, x2, x3 and x1 plus x1 dash, x2 plus x2 dash and x3 plus x3 dash, the properties are same. This is called macroscopic homogeneity. So the invariance of homogeneity or composition means that the properties, they are invariant under a arbitrary translation of the origin. This is one important property. The next important property which characterizes the crystalline material or single crystals, and they are of immense practical importance, practical use, are the anisotropic nature of the crystalline materials. It may seem contradictory to you when they have macroscopic homogeneity and anisotropy. So macroscopic homogeneity is mainly concerned with the composition. If you have a silicon dioxide crystal, SiO2, then all parts of the crystal will have a composition SiO2. It is not going to change. But there are certain properties of that crystal that are direction dependent, or they are not scalar. Scalar means it is invariant in all directions. It is same in all directions. And some of the properties are thermal properties, some conductivities, refractive index, dielectric property, magnetic susceptibility. They are direction dependent. Now what happens? What happens if the effect and the reaction of the crystal, they have a directional nature or a directional or vectorial relationship? For example, if you have a crystal like this, you must have heard about piezoelectric crystals. Now suppose you are applying the force in this direction, and due to the force in this direction, there is an electric field that is induced. Electric field that is induced in this direction. This is the direction of electric field. So this force and electric field, they are perpendicular to each other, or they can have any direction dependence. Suppose if you are applying the force here, and the electric field, it is coming out through, it is being produced in this direction. So the effect and the reaction of the crystal, they are related by direction. They have a direction dependence which you call the vectorial dependence. Then this is described by a tensor quantity, Maxwell's stress tensor. It is one example that you study in electrodynamics. Piezoelectric crystal, refractive index, they have these properties. So when you have an isotropic material, this means a particular property P. If this is a property P, if this property is independent of the orientation of the crystal or the independent of the orientation of the frame of reference, the matter is said to be isotropic. Means same properties in all directions. Homogeneity means all parts. So you have to be very careful in the definition. Isotropy means same properties in all directions. This is called isotropy. So liquids and gases, they are isotropic, but crystals are isotropic with respect to some properties only, or you can say that crystals are anisotropic in most of the cases. Let me write this: crystals are anisotropic in most of the properties. Most of the properties of crystals are anisotropic, and that is why they find large amount of application in industry and in technology. Now, when you have a property that is direction dependent, and you need to define the orientation or the direction to describe the property, it is called anisotropy, and crystals are anisotropic. One example, practical life example I am showing you. This is the picture of a gemstone. It is blue sapphire. Blue sapphire. Sapphire is a gemstone. It has a particular composition. So when the jewelers or the gem cutters, they polish the stone, they have to see in which direction they should cut the stone so that it has maximum shine. So the optical properties of the gemstones, they are very interesting things. They are anisotropic. In a particular direction, when the stone is cut, it is shining very brightly, and on the other direction it is not shining so brightly. So it is an anisotropic property. The next important property is this symmetry, and this describes all the content of your syllabus. We will go in more detail of this topic, but let us have an introductory lecture, or let us introduce ourselves to the concept of symmetry in crystals. Now what happens? Symmetry, I think most of you know what is symmetry and what is antisymmetry or asymmetry. A huge amount of data, or what I should say, there are many topics in high energy physics that are related to symmetry, but I am not going to those complex mathematical complex things. From the layman's point of view, or from whatever you have studied in school, you can see this is symmetric and this one is asymmetric. Means the two parts of this diagram, A and B, if they are superimposed on each other, they will exactly cover each other. They will overlap. A and B overlap. And this is the thing you read in study in school, that is congruency. Congruency of triangles, similarity of triangles, these are the topics in geometry that you study in school. However, this diagram, in this diagram, A and B are not overlapping and they are said to be incongruent. This is symmetry. There are many symmetrical diagrams, many symmetrical objects that are found around us, but we are talking about the crystals. This is another example of symmetric objects. Now, you can see all these objects, you have a border line, demarcating line, and about this line, the two parts are overlapping on each other. Now let us see, what does symmetry mean in crystal? What is this concept of symmetry in crystals? Symmetry is a natural property, most general and fundamental concept of physics and natural science, and entire crystallography is based on symmetry. Crystallography means study of crystals. Crystallography is the study of the structure of crystals. Structure means microscopic atomic level structure. Structure of crystals. An entire crystallography is based on this word, on certain words I should say. The first one is symmetry. Then you have repetition. Repetition will repeat itself many times. Periodicity. These are the words that form the fundamental structure of your crystallography. Now, symmetry is the most general law that is inherent in the structure and property of a crystalline substance. And that is why it is sometimes said that symmetry is the property of crystals only, but there are other kinds of symmetry in nature also. Now, what we mean by symmetry in crystals is that this is a structural diagram of quartz, SiO2, quartz crystal. And you can see here there are many things that are written on this structure, M, Y2, Y2U. So you will study these things. What are these? Now this structure, this SiO2 or quartz, it has a property that if you are rotating this structure around the vertical axis 3, if you are rotating this by 120 degree, the structure will overlap on itself. Means the motion, the rotation by 120 degree about the axis 3, it appears to change nothing, but a motion has occurred. Now when a motion is occurring, but it appears that there is nothing has changed, this is called symmetry. The possibility of transformation of an object which brings it to self-coincidence to a new position. This is called symmetry. Let me write this. A rotation of 120 degree around axis 3 brings the crystal to self-congruence or self-coincidence. Crystal to self-coincidence means after 120 degree rotation about axis 3, the crystal overlaps or it is congruent, crystal overlaps on itself, or it is congruent with itself. This is called symmetry. Let me give you a more simple example. You must have studied, and this concept I will use in detail in the next lectures. Translation motion. Now what happens in translation motion? You are at point 1, you move by some distance a, and more correctly it is uniform motion. Suppose it is uniform motion. This is point A, you move by some distance a, you reach to the point 2. So you are the same person, the person is here, suppose this is the person. This person moves a distance a and reaches point 2. This person is not changing. The same, these two, although the diagram is not proper, these two persons can overlap on each other. They are congruent with each other. So it appears that no motion has occurred. So walking by a distance a along the horizontal axis or any axis, reaching this point 2 is same as the situation that this person was at point 2 from beginning. Now suppose again he moves a distance 3 by he moves a distance a and reaches this point 3. Again, he is the same person. Most important, the environment around him, it is same at positions 1, 2 and 3. This means if the distance a is not considerable, it appears that the same person is present at 1, 2 and 3, or no motion has occurred. This is called symmetry. I will describe this thing in a more detail. Symmetry means after a transformation, it may be rotation, it may be translation, it may be reflection, inversion, anything, that after a transformation, everything remains same. This is the most simple meaning of symmetry. If you are rotating this crystal by 120 degree, after rotation by 120 degree, what you will see? A copy paste image of this crystal structure. This is after 120 degree rotation. Let me make the sizes same. So when I am putting this diagram on this diagram, this is a single diagram. This is the magic of symmetry. Let me explain you again. Suppose this is the crystal and you are rotating it by 120 degree in this direction. You get this crystal. And when you overlap these two things, they are same. They are exactly overlapping. But if you are rotating by some different angle, suppose you are rotating by 190 degree, it may be that this diagram and this diagram are not overlapping. They are like this. So this is incongruency. So 190 degree is not producing the congruence. 120 degree is producing the congruence. This is symmetry. So we will study the concept of symmetry and periodicity of crystals in detail in the next lecture. For the time being, please stay tuned, like, share and subscribe the videos and send your valuable comments. Thank you.